Yeah. All right. The soothing sounds of Mr. Clark talking calculus. Yes, right. So, and I want it to be known that I did not give my wife that sweater that she's wearing today, just so everybody knows, okay? She claims my mom did, and maybe she did, but, all right, so what was I gonna get here? Okay, this right here. So so are there any questions before 13 through 26? And maybe there's not any questions there, but we should at least go through the answers quickly. Anything before number 13? Okay. Anything? 7. Okay. 7 talks about the absolute value of x. And so on 7, but the questions, and several people did ask me about this yesterday, they give you the function is absolute value of x. Now I think it would be important, it would be helpful if you knew what that graph looked like, right? So it's the old V graph like this. Okay, so I think that would be helpful. But then when they ask you the limit questions, they ask you, like, what's the first one? They ask 0 from the right, with the little plus, but then they ask about f prime. Well, keep in mind, whenever they ask for a limit, they're asking for what these outputs are as the input approaches here. Well, what are the outputs of f prime? What are the outputs of f prime? Well, but I mean just in general. The slopes of f, right? So what this is saying is, what are the slopes approaching, or what are the slopes when this graph approaches 0 from the right? Well, from the right, what's the slope right there? Right? 1, 1, 1. So as you approach 0 from the right, the slopes are not only approaching 1, they are 1, right? And so the answer there is 1. Now, somebody had asked me, though, about this. They said, could you graph f prime? Well, you could. I don't think you have to, but you sure could. What would the graph, if this is f, what would f prime look like? Did we draw this yesterday? I thought I did. Okay. So if you wanted to do that, that's fine. And so as you approach 0 from the right, that's like the car driving in here. Well, he's coming in at 1. Now we're looking at the outputs, not the slopes. So here we're looking at the slopes. Here we're looking at the outputs because this is the f prime graph. So from the right, it's 1. From the left, it's -1. So the limit does not exist right here. Okay? Well, remember how we said the derivative does not exist at a sharp point? Well, that's why. Because this is kind of like asking that same question. What's the limit of f prime? It's kind of like saying, what are the y values? What are the slopes approaching? Well, from this side, the slopes are approaching -1. From this side, they're approaching 1. The limit does not exist. Therefore, the derivative does not exist. So there is kind of a connection right there as well. Okay? So that's kind of what problem 7 is about. All right, let's just run through 13. Now, one of the things we're going to talk about later today is this idea of continuity, a continuous function. It's really nice to know that a function's continuous. And if a function's continuous, it just means it's smooth. Well, I shouldn't even say smooth. Absolute value graph is continuous. It's not smooth. It's got that sharp point in it. But continuous means there's no breaks or no jumps or no gaps, no holes, nothing weird going on. It's just, you never have to lift your pencil, really, kind of a thing. I mean, that's a very informal way of saying it, but it's just nothing weird, like a parabola or a cubic or a sine graph or, an absolute value. I mean, it's just kind of, it's continuous. I mean, it just keeps going, and you don't have to lift your pencil. Now, the square root graph would also be continuous. I don't want to get into too much of it yet because we're going to do this later, but the square root, I shouldn't say just goes on and on forever. It wouldn't have to. Like the square root graph that's continuous. Even though it stops right there, it's just no breaks, nothing weird happening. It's just that it doesn't have anything to the left of 0 because you can't put a negative in a square root. That's its natural domain. Okay? So that's continuous, all right? But this graph is clearly not. I mean, this graph clearly has a lot of weird stuff going on. Okay? It's got these holes, and it's got dots everywhere, and it's got breaks and going on in there, whatever. Okay? So a lot of weird stuff going on. Or we might say interesting stuff going on, okay? And so when it comes to a limit question, those are the interesting places. So anyway, we'll come back and look at this graph a little later. So on 13, they ask what? again, when we got a graph, I think we think about the video yesterday, we picture the cars. So 13, as x approaches 0, what's the limit? 2. Everybody feel good about that? As x approaches 0, the cars are coming right in there at a height of 2. All right, how about negative 3? Cars are coming right in there and they're meeting at negative 1, even though the diner is not there, right? Like we saw in the video yesterday. It's up there, it doesn't matter. The cars are approaching negative 1, so the limit is negative 1. Okay, next one, negative 1. Limit as x approaches negative 1 does not exist. The car on the left is approaching 1. On the right, you're approaching 2. They're not the same. Limit does not exist. Okay? How about next one? 2 from the left. 2 from the left, it's approaching 1. Next one says 2 from the right. Approaching 1. Well, that's important. If from the left it approaches 1 and from the right it approaches 1, next question, number 18, what's the limit as x approaches 2? 1. See, that's what I call a normal limit. Number 18 is a normal limit as x approaches 2. What that means is both cars. Both cars have to come in and meet. When you're talking about just from the left or just from the right, you're just talking about one of the cars. And they'll always approach somewhere. But the question is, do they meet? And that's what 18 is about. And they do. They meet at 1. Okay, what about 19? Negative 2 from the left. 0. Yeah, it's approaching 0. Okay, what about the next one? 1 from the right. 1 from the right, that car there is approaching 0. Absolutely. Okay, next one, negative 4 from the right. Negative 4 from the right, car is coming down here. It's reaching a height of negative 2. Okay, 22, 4 from the left. Negative 1, negative 1, height of negative 1. Okay, then we get in the last group of them here, we get into this F prime business. Now that's just like we were talking about earlier. So now we're talking about the slopes. Now we're talking about the slopes, okay? So what about as x approaches 3? What are the slopes here? Yeah, on the left of 3, they're negative 1. On the right of 3, they're negative 1. So the slopes are approaching negative 1, or they are negative 1. Not only approaching, but they are. So that's negative 1. Okay, next one. Negative 1 from the right. What are the slopes? 0. 0. Okay, negative 1 from the left. 1. Right? So slope on this side is 1. Slope on this side. So what would be the limit at negative 1 of f prime? Does not exist. Because on this side the slopes are 1. On this side the slopes are 0. And so it does not exist. Okay? All right. And then what about negative 3? What's the slopes on this side? 1. What are the slopes on this side? 1. So what's the limit? Would it be 1? So on 26 it'd be 1. So as x approaches negative 3 on both sides, slopes are 1. The slopes now, okay, on those last 4 questions, we were talking about the slopes of this graph. We're talking about f prime. Okay, so that's different.
So if the slopes on the right side and left side are different, then that means it has to be.
Then it does not exist. Right, if the slopes on the left and right side are different, so on this side the slope is different than on this side. See, so for example, we could, so what would be one that would look kind of strange? If you had a graph coming in here, and that was a slope of 1, and then the graph took off and went up like that, they were both slope of 1, right? On this side the slope's 1, on this side the slope's 1, so the limit of f prime on that graph would be 1.
So then at 2, since the slopes, and even though they go in the same spot,
Yes.
slopes are different.
Good, Craig. If they would have asked about f prime at 2, we would have said does not exist. Because on this side, the slopes are positive. I don't know what they are for sure because it's curving. And on this side, they're negative, so they wouldn't exist there either. Does not exist. Which is kind of like the absolute value graph we just talked about, the V graph. On this side, the slopes are 1. On this side, the slopes are negative 1. So at that sharp point, it doesn't exist. And that's what we have. Okay? All right. And then 39 through 42. Now, on this one, you know, people have asked me, should you draw a graph on this one? Well, you could. You know, you could draw a graph on this one, but I don't think it matters. You don't have to. Basically, what you have going on here is you have a parabola that's coming in. It's kind of curved down. I don't know exactly where it ends up or whatever. But and then at 2, and that's the important part, the parabola is here when x is less than 2. And when it's greater than or equal to 2, you got this line. And now maybe the line So we got an open circle there. Maybe the line takes off. Maybe it's that. I don't know. Maybe this line takes off right from here. You know, might do that. We don't really know without graphing it. I don't think I need to graph it. If you want to, go ahead. But it may not need it. So let's talk about that. So what's the first one asked? The limit as x approaches what? 3. Well, where are we going to be on this? Remember, that's 2 right there. Yeah, we're going to be on the line here somewhere. Well, is that limit going to exist? Are those cars going to meet? Sure, they're just going to meet at whatever that point is on the line. So what was it? 3x minus 5? So you put a 3 in there. 9 minus 5 is 4. So the limit's going to be 4. So I don't think you needed the graph, though, to know that. You just look at, well, as x approaches 3, I'll be in this range right here, greater than or equal to 2. I'll be on the line. And the line has nothing weird going on it. The cars are going to meet anywhere on the line, whatever the point is. Okay, what was the next one? X approaches 0. Well, now you're going to be back here on the parabola, right? So when x is 0, you're back here. So you just plug 0 into the parabola and you get what? 3. Okay? So that's where the cars are meeting there. And then, of course, the one that's the most interesting is as x approaches 2. What's going to happen? Well, how do you tell if they meet here now? Plug them in, right? Well, one's open, but really it doesn't matter. I mean, we just got to plug them in, right? Because maybe it's this situation. Maybe the line takes off right from there. Then they meet right there, and the limit would exist. If there's a break like this, then the limit wouldn't exist. So we're going to do what? Plug it into both of them, right? We got to plug the 2 into both of them because that's where the break is. So you plug a 2 into this, and you get 1. And what do you get when you plug it into this one? Also 1. So it must be this scenario here. They must meet at 1, at a y value of 1. So as x approaches 2, both of these meet at 1, so the limit is 1. Okay? And was that it? Was there one more? There was one more. What was it? X approaches 1. Well, where's that at? That's back here on the parabola as well, right? That's back there on the parabola. So you plug a 1 into the parabola and you get 2.5, positive 2.5. I saw a lot of people's paper had negative 2, so I'm not sure where that came from. Oh, you put it in the wrong one. Put it in there. I saw people had negative 2. You must have put it in there. X approaches 1 is when x is less than 2. Okay? So when x is less than 2, you're on the parabola, not on the line. So you plug it into the parabola. Okay? So I don't think you needed the picture. I mean, if you drew it and it worked out for you, fine. But, that's good. But you wouldn't need it. But at least you're visualizing what's going on. Okay. That's pretty much it for the homework. Let's take a look. Let's review a couple of things here. We did this in the other class. This didn't work out too bad. Let's go to this website here. So just get some your notes out or whatever. We'll just practice. We'll do a couple of derivative practice ones here from the website. Let's see if I can find some decent ones. Just on using our shortcuts. Here's a good one right here. Okay, do this one. Here's your function 2 square root of x over x to the 5th. 2 square root of x over x to the 5th. And we want to find f prime. Okay? Go ahead and do it. Okay? Now, hopefully, hopefully, whoops, freezing here. Hopefully you recognize that you've got to do what with this before you do your derivative? Change it into some sort of, I mean, this would have to be what, 1/2? Isn't there more you have to do though? Move that up there as -5 or subtract the powers, however you want to do it. So really this is 2x to the -9/2. You need to do all that before you can do the derivative. Okay, now I would think of this as I would subtract there, so I would have thought of that as 1/2 take away 10/2. So that's -9/2. You can bring it up, whatever. Okay, so now when you do your derivative, you get what? -9x to the -11/2 is what you should have had for that answer. And we want to use fractions like that, not decimals, not mixed numbers, but improper fractions. Okay? And now I'm not going to have a big emphasis on having to simplify that stuff algebraically, but maybe, but you may have to do some of that. Some of these we can't do on here yet. Why was it 11? Well, because it was 9/2. -9/2 take away 1, so we take away 2. Okay. Some of these we could do, some of them not so much. Let me take off the sine and cosine here for a minute. We'll do one of those in a minute. Let's move up to 3. Maybe it'd be better. Oh, whoops. I meant to go backwards. But there we go. Let's do this one, and then I'll make up one maybe a little more. 8x to the 5th plus 8 square root of x times x squared. So that last one, there's a times there. Eight x to the 5th plus 8 square root of x times x squared. So get that written down, and then I'm going to do a little work up here. So if you don't want any hints, don't look up here. I've got the answer up here if you want to look. If not, I think I've got the answer. And if you go to this website, you can type them in. But there are a number of these that we can't do yet, and we'll do it. And so as we learn more of the rules and get in Chapter 3, this will be a little more useful. We'll get into, we'll be able to do most of them that are on here. So then, so I don't know how useful this is to go on to right now, but it can give you a little bit of practice. Okay, any questions on that one? All right.
Did you get the 8x?
Which one? Yeah, because these two have to multiply. So I have to add the 1/2 with the 2. That'd make 5 halves. So yeah, I have to. So it's basically this term plus that term. So that's where that comes from. And then 5 halves down in front. And remember, when you multiply an improper, I just think it's a lot easier to deal with that. When you take 5 halves times 8, remember, that's like 8 over 1. So you just multiply the tops. So you have 40 halves, which is 20. So that's where the 20 comes from. And then subtract 1 from 5 halves to 3. Okay, let's do one here. Oops. I'll just make one up here. Let's do this. Okay, so let's say we got f of x. Let's do (2x plus 3 to the 5th minus the cube root of 3x plus 2 sine x. Try that. Okay, if you don't want to look yet, don't look. Okay, any questions there? Remember to kick out the 2 here. Kick out the 3 there, right? Because that compresses the graph whenever you're multiplying on the inside. You have to kick out. Yeah. When it's attached to the x. That's a good way to say it. Okay? When it's inside the function. Now, somebody had asked this. The example I gave in the other class was a little different. I had something like this. I had 4x to the 7th or something. You had to kick out a 4 on that, right? You bring the 7 down in front. 4x would be left alone to the 6, and then you kick out a 4 because it's on the inside. Now, if that would have been 4x to the 7th without parentheses, that's different, right? The 4 isn't really attached to the x here, is it? It's attached to what? X to the 7th, right? It's different. It's not attached. So the 4 is on the outside here as opposed to being on the inside there. And so that's an important distinction. So here, when you bring down the 7, you would just have 28x to the 6, and that'd be it. Okay, so there is a difference between the inside and the outside. Yes? Well, yeah, because the 3's on the inside with the x. You know what I mean? So since that 3's in there, that's why it went in parentheses. If this would have been 3 cube root of x like that, then this would have been 3 and then the x is to the 1/3, but not the 3. And so that would have been the difference. Yeah, that's the difference. Yeah, and again, and that's kind of why I picked those, so we could talk about that. Okay, and then make sure you simplify. The 5 and the 2 go together to make a 10, and the 3 and the 1/3 make just a 1, and then, of course, 2 sine x would be 2 cosine. Okay, so just some of those kind of things right there. All right, now, something from section 2.1. That was kind of from section 2.2. Let's start with, let's start with f of x equals 2x squared minus 3x. And I want you to find f prime of 3 using the definition of the derivative. The long one. That right there. Yes. Yes. You have to know the definition of the derivative. Now, we will not use that one. Okay? But that one right there. Now, there's two different things I might ask you related to definition of the derivative. I might ask you for f prime of 3, or I might ask you for f prime of x using the definition of the derivative. Right now, let's do f prime of 3, and then we'll talk about the differences. Yeah. So right now, we're doing f prime of 3 by the definition of the derivative. If you need to talk with a partner or something, you can while you're going. And then here in a few minutes, I'll start writing up what you should have, so don't look if you want to try to get it yourself. Richard, you got this all figured out here? Here, hit him in the tapping. Be nice. Got this all figured out there, man? Visualizing it in your sleep. Thought you're going to fall over a couple times there. Okay, I'm going to start writing some stuff up here, so if you don't want to see, don't. Anybody get the final answer? I heard 9, I heard 15. Those are the two common answers. More people are getting 9 than 15, so by majority rule. Here's where you, if you had 15, here's where you went wrong. Which is the same thing I always say where we go wrong, right? Distributing a negative. -9, minus 3/8 right there. Okay? So it should be 9. Now, we're finding f prime of 3. According to the shortcut, we should be able to do this really easy, right? According to the shortcut, what's f prime of x? 4x minus 3, right? The shortcut says it's 4x minus 3. And then couldn't you just plug a 3 into that then? 4x minus 3, that's f prime of x. So f prime of 3 would be a 3 plugged in. So 4 times 3 is 12. 12 minus 3 is 9. So it should be 9, right? All right. So anyway, I've got this. I always said set it up with your f notation first. What we do is, since we're doing f prime of 3, we put a 3 in for x right there, not in for h. Somebody in the other class said something about putting a 3 in for h. No, h always goes to 0, right? H always is there late, it goes to 0 because we're letting the 2 points get really close. H is the distance between the 2 points. So as h goes to 0, the 2 points become 1. So that's why it's h goes to 0. So that doesn't have anything to do with the 3. The 3 goes in there where the x is. And so then right here, we plug that into this function everywhere we see an x. So that's that whole blue thing. Here's the whole red part. Okay, and then it's just a bunch of algebra, a bunch of foiling out, distributing, combining like terms. The 18 goes away with the minus 9, minus 9. The 12h minus the 3h gives us a 9h. And we cancel our h's. Then we can put a 0 in for h. And when we put a 0 in for h, we get 9. So you have to be able to do that. Now, what would be different if I would have said find f prime of x? Yeah, this would have been an x plus h right here. This would have been an x right here. And then this would have had a bunch of x plus h's, and there would have been x h's and x squared h's and stuff like that, and things would have canceled. And what would we have gotten after going through the whole process? We'd ended up with what? We'd ended up with 4x minus 3 after going through that whole process, canceling h's and then putting a 0 in for h. We'd ended up with 4x minus 3, which of course we know we should end up with because we know by the shortcut. Okay? So you may have to do 1 or 2 of those on the quiz. You know, one where you do f prime of, say, 3, one where you do f prime of x, you know, one of, no more than twice, I don't think I'd have you do it, but possibly one time. Now, that was factoring and canceling. We also did some with conjugate. We did some with common denominator. We're going to get a chance to practice some of those algebraically here in a minute. Yes? Yes, but not right now. Not this minute. But that's be certainly one you could jot down and try with this same function. And to be honest, I'll probably, for the most part, keep it fairly simple. You can almost make up your own where you can just do some variation of an x squared and an x, or just an x. You know, I probably won't get into like an x cubed or an x to the 4th, because then that's just more foiling out, whatever. But keep it into an x squared and, you know, that kind of thing. So you can make up functions that are a variation of this and just play with them and see.
What's the wording for the long method?
The definition of the derivative. The definite, and well, I won't be here, I guess, to tell you when I pass out the quiz. So there you. So that's pretty important. Write that down. You know, make a note of yourself to yourself. The definition of the derivative. That means, that's the hint that means do it the long way. And there would be no more than 2 of those on there. No more than 2 of those would you have to do that. Okay, the definition of the derivative. All right. Otherwise, it would be just shortcuts. Find a formula for f prime, find f prime, that kind of thing. It doesn't say definition of derivative. Then that's just shortcut. And you would reckon, I mean, certainly if I gave you this function and said find f prime, you would hopefully look at that and know, I don't think he wants us to do that by the definition of the derivative, okay? That would really be a mess. I mean, you just wouldn't be able to do it. So, all right, let's take a look at some things that were on the video last time, some limit problems. Let's go through some simple, we talked about graphs on today's homework, that worksheet the other day, and we did a little bit yesterday with the tables, so we'll maybe do one of those here real quick. So have your calculators handy. But let's do one with algebra first of all. So if we did, so let's say we had this problem right here. Limit as x approaches 2 of x minus 3 over x plus 1. Let's say we had that problem right there. Okay? Give you 5 seconds to get the answer. What's the answer? Negative 1/3. How'd you get it? Direct substitution, right? The very first thing you do, especially on these algebraic type ones, is you do direct substitution. So you plug a 2 in, you get negative 1/3. Now get your calculators out. We'll make somebody the presenter here real quick. And Brittany. All right. So so what I want to do is I want to show by the calculator method. Now, a simple one like this, I wouldn't have to do on a calculator anyway. But let's just review that table method that we did the other day. So we want to do this one with a table on the calculator. So where does she go first? Where? Go to the graph screen. Okay, and she's still got her table up there from yesterday, which is great. And now it's gone, but that's fine. Now we'll go into F1, and we're going to put in our equation. So she clicked over there and delete the old one out. Okay, here we go. And she's putting in that function that we're doing the limit of. We want to look at those outputs, and we want to look at it as x approaches 2. And she's got 2 in her table, but is that table sufficient? Is that table showing that the limit is negative 1/3? I really don't think so. I mean, yeah, you've got the value there. This one does work with direct substitution. What did we always usually see in our table when in that middle row? We usually saw undefined, right? But that's because we were getting 0 divided by 0, wasn't it? On this one, direct substitution worked. But really, to show the limit exists, we really need to see that the 2 cars are coming together, right? So we really need to be able to see the left and the right. So what do we do next? We want to click inside of our table so that our table is highlighted. I think would be good. I'm not sure you have to, but now you can go to menu, and then you go to table, and then you go to table settings. You're going to have a worksheet with some of these on it today where you draw the table out, and you're going to have some of these on your calculator, part of your quiz. And we want to start the table where? At 2, because we're wanting to know as x approaches 2. And then what about our table step? 0.0001. Now again, I'm not going to be here to go over these directions and stuff during the quiz. It should be clear. It's I mean, that's why we're going over these things now. Why we'll be talking about them again on tomorrow. All right, go ahead and hit OK. And then she wants to do what from here? Arrow up a couple, because we want that 2 to be right in the middle. That way we can see on the left and the right. That is the data that shows us that negative 1/3 seems to be the limit. Somebody in the other class said this, and I think it was Garrett. But I actually like what he said. He said, why couldn't you just take, without doing the calculator, he said, couldn't you just take like 2.0001 and plug it in, and 1.999 and plug it in? Couldn't you though? I mean, isn't that the same thing? I mean, that's what the table is. The table is plugging in 1.999. But I like the fact he said that in the sense of, by saying that, it kind of shows, you kind of got the idea of what the limit is. It's not technically one of the things that I put down here as far as doing it. But, I mean, that's what we're doing when we do the table. It's just we're letting the calculator do most of that work for us, right? And so, and if this is a no calculator one, of course, who wants to put in 2.001 and 1.999? I mean, you're not going to do that, right? So it's just direct substitution works. But I like the fact that he's thinking that way, because that is correct. I mean, and so that shows maybe that you understand a little bit about what you're trying to do here. Okay, so let's go to this one. So try this one here. So let's say we got limit as x approaches 3, x squared minus 9 over x minus 3. Okay, I'll give you 15 seconds to do this one. Now, I'm talking without a calculator, right? Without a calculator. I mean, we can put it in the calculator. You can go into F1. You can go ahead and put it in there, Brittany. But, okay? Just as a double check, we'll just check it this way. Okay, what do you got? 6, right? And the algebra is probably so easy that you could just do that one in your head without even looking. But what's the algebra that you do? Okay, let me back up. First, you try to direct substitute, right? And you put in a 3, and what do you get? You're going to get 0 divided by 0, right? Now, 0 divided by 0 is kind of the magic number here. Okay? When you do 0 divided by 0, now, Brittany, leave your screen just the way it is. When you get 0 divided by 0, that's kind of the magic number that says, hey, there's probably an answer. Maybe not, but there's probably an answer. I got to keep going, okay, and do, in this case, some algebra. So we factor x minus 3, x plus 3, and we divide out the x minus 3, and that's like canceling the h. Now we plug the 3 in. 3 plus 3 is 6, and so the answer is 6. Yes?
So, you know, when it's 0 over 0, there's probably an answer. Is there any way you know that there is no answer?
There is. Okay, great question. Everybody here at the Thai I just said that when you get 0, 0, there's probably an answer. You keep going. But how do you tell if maybe there's not an answer? And here's how, for at least for right now. Now, we'll get into the specifics of this more later on. But there's another way something can be undefined, and that could be 2 over 0, or 3 over 0, or negative 7 over 0, or, you know, dot, dot, dot. Any of those possibilities. That's also undefined, but that means, for right now, if we get that, we're going to just say does not exist. The limit does not exist. Now, actually, what's going on is it means infinity or negative infinity, and it means that there's probably an asymptote kind of thing going on. But we're going to get into those more in Chapter 4, the asymptote and the infinity stuff. So for right now, and I think there are some on the worksheet that I give you today on the homework. I think there might be a few where you get, like, you plug in and you get 2 over 0. If you get that, it's okay right now to just say does not exist. The limit does not exist. Okay? But if you get 0 over 0, keep going. And you're probably going to find an answer. But if you don't, here's what might happen. You might get 0 over 0, then you factor and you cancel, and then you plug in, and then you get 3 over 0. That's when you would know, okay, it doesn't exist. Okay? All right. Let's go back to the calculator screen. And Brittany has got, hopefully, 6. Oh. She's got 5. Wait a minute. I thought the answer was 6. Aha, that's what x approaches 2. Very good. Okay, so she needs to go to her table setup again. Her table. I think you can do it from there. I think you can do it your table settings there too. It's just a different looking menu, but I think that it's the same table settings. So, so now she wants to start at 3, right? Because that's where x is approaching, and then that's probably okay. That could probably, yeah, that's okay. That was still there, and then. Yeah. And there you go. And so arrow up a couple, and it is undefined, but again, we don't care. That's like there's a hole in the graph there. We don't care that it's undefined there. What we care about are what these are, and that's where the cars are coming in, and they're coming in at 6, so that looks good. Okay, so that's good enough. This is probably, thank you, Brittany. And, okay, so let's do one more here. No, we'll do 2 more. Let's do the limit as x approaches 4 of square root x minus 2 all over x minus 4. I'll give you a minute to do this. Now, we've done direct substitution. Think about the video. We've done direct substitution. We've done factoring. What else we learned yesterday? Well, we knew it before, but we did the video. Conjugate method, which is always a big hint whenever you see a square root in there, to think of the conjugate method. Try that. Now you got 40 seconds. Okay, what do you got? 1/4. What's the conjugate? Square root of x plus 2. Now, x plus 4 would be the conjugate of the bottom. The only difference is that doesn't really help us any. We want to do the conjugate with the square root one. It doesn't matter if it's on the top or the bottom. It doesn't matter. Okay, wherever the square root is, that's the one we want to do. So when we FOIL this top, we get what? X minus 4. The bottom, we should not multiply out. We usually want to keep that left alone because we're hoping something cancels. And of course, it does. X minus 4 cancels and we're left with 1. Then what? Now you can plug the 4 in. That canceling is what we wanted to happen, kind of like the H canceling. Plug the 4 in. Square root of 4 is 2, plus 2 is 4, but it's on the bottom. You get 1/4. Don't put 4. I've seen that before on quizzes where we have a problem similar to this, and they get all done and they plug the thing and they get 4 and they forget that it's on the bottom of the 1. So that'd be 1/4. Okay, one more. Yes.
Probably went over this before, but what if, like, since the square root can also be -2, and that cancel out to 0 on the bottom?
Well, not usually, because if it would have, you mean, no. Oh yeah, we have talked about that before. Square root of 4 is not 2 or -2. Square root of 4 is just 2. If there's a negative in front of it, then it's -2. What you're thinking of is the solution to this equation. The solution to that equation is plus or minus square root of 4. Yeah, but if I write square root of 4, it's just 2. All right, here's the last one. Limit as x approaches 3 of 1/3 minus 1/6 minus x all over x minus 3. Try that. I'll give you a couple of minutes to do this. Okay, we had factoring, we had conjugate, and then we had get a common denominator. Bow tie or get a common denominator. Okay, I'll give you 2 minutes to either get it or give up. Oh, oops, look at that. Okay, is that enough time to get it or give up? One or the other?
Or get it.
Or, yeah. Okay, gee, no fighting. Get some bullying going on in here, it sounds like. Oh, you guys probably, did you guys talk about bowling in Bearcat then?
Oh, it was in marketing, somebody
Oh,
gave
it's
a
marketing.
presentation
Oh,
on an issue of the school.
I see. I have freshmen in Bearcat, so we did some bowling. We did some bowling, so we did some bowling today. We did some bowling. All right. So common denominator. Of course, I know all about bowling because I like math in high school. Nerds. Yeah. All right.
She got it after I explained.
I see. And then now she's envisioning me in high school.
Did
Big glasses.
you wear suspenders?
No, but I had my calculator in my pockets.
Did you really?
Because back then they were big calculators.
Back then.
Yeah, they were big, but they came in like carrying cases and they had loops where you could put on your belt, and so you could have a graph.
I had that.
I did not know, but they actually had loops.
Was it like this?
I don't know. Yeah.
Did you have pens?
They had the, what's that?
Did you have pens?
The pins. Oh yeah, the pins. I know I did. But common denominators. That's what we were talking about. All right. Now, for a minute, I'm thinking back to high school. Luckily, I can't hardly think back that far anymore. So, all right. What is the common denominator? Yeah, and you can multiply together, or you don't have to. You can just leave it alone, right? Now, just to refresh your memory, what we talked about is like if I had 1/4 minus 3/7, the common denominator is 4 times 7. It's just this one times this one. So that's 28. So the common denominator is going to be 28. Just that one times that one. And then you say, well, how do I make this into a 28? Well, I got to take it times the other one, top and bottom. How do I make this 7 into 28? I got to take it times the other one, top and bottom. Well, that's the same thing we do here. The common denominator up here on top. Okay, here's the x minus 3. On top, the common denominator is going to be 3 times 6 minus x. Okay, so it's just going to be 3 times 6 minus x. All right, you can distribute it or not. It doesn't matter. A lot of times I leave a factor in case something's going to cancel, but probably not here. So what do I need? On this one, I need the other one. So I need to multiply by 6 minus x. Just like here, I have the 4. I need to multiply the top and bottom by the 7. Okay, and here I've got the 6 minus x, but I need to multiply top and bottom by the 3. Okay, so that way both fractions have the same denominator. And then up here, what would I have? I'd have 7 minus 12, right? So up here, I'm going to have 6 minus x, and then minus 3. Okay? So when I look at that, that's going to be what? 3 minus x up there, and then over this denominator, and then all over the x minus 3. So now what I have is a fraction divided by something. So that's kind of like having 2/3 divided by 8. Well, if you've got 2/3 divided by 8, you don't divide by 8. Instead, you multiply by 1/8. You multiply by the reciprocal. So what we're going to do is instead of dividing by x minus 3, we're going to multiply by 1 over x minus 3. Multiply by the reciprocal. Now what we hoped would happen is that these would cancel. They almost do. It's kind of like an 8 and a negative 8 canceling. They do, except there's a negative 1 still there. The 8's cancel, but there's a negative 1. Well, that's what we have here. I can factor out a negative 1 from this. If I factor out a negative 1, that would be negative 3 plus x, right? Factor out negative 1, it'd be negative 3 plus x, which is x minus 3. So the x minus 3 then cancels the x minus 3, but I have a negative 1. So I have negative 1 over 3 parentheses 6 minus x. Now what? This is one of those examples of you get so wrapped up in all the algebra you kind of forget what you were doing. Now we can put our 3 in for x. Because we canceled out this is what was causing the 0. Okay? So now I can put in the 3, and so 6 minus 3 is 3. 3 times 3 is 9. Negative 1, 9. Okay? All right. And if we were to put that one into the calculator, we would see that it was negative 1/9, whatever that decimal would be. Negative 1 point repeating. Okay? So, That's commented. Now, I've got an extra, I can bring it tomorrow. I've got an extra algebra sheet that I just round up a couple of old algebra sheets, like reviewing common denominators and reviewing conjugate type things that might be helpful. It was mostly common denominator things that you might find helpful. Okay, there's one last thing, and then I'll let you get started on homework here. This is kind of new, a little bit new, related to what we're doing, though. Page 106. Turn in your book to page 106, please. And on page 106, we had this graph right here. Or not on page 106, but in our homework today, 110, 111, we had this graph right here. And we were talking earlier today about continuous functions. One of the things I will ask you on the quiz is, where is this function discontinuous, which means not continuous? And we were talking about continuous means no breaks, no gaps, no weird things happening, right? This one is clearly not continuous in a bunch of places. Now right here it's continuous. There's nothing bad going on right here or right through here or up here, right? But there are clearly some places where this is not continuous. So first of all, if I ask you, where is this discontinuous, at what x values, you'd say what?
-3.
-3.
-1.
-1.
1, 2, 4.
And 4. Bunch of them, right? It's discontinuous in all those places. But the other part that I will have you say, or I want you to say, is why is it discontinuous there? And I want to use more technical language, not just informal, well, there's a hole, or there's a break, or there's a gap, or whatever. You have to lift your pencil, that kind of thing. Okay? So we're going to write down, what does it take to make a function continuous? There's 3 items that it has to have. And if it's missing any one of those 3, that's why it's discontinuous. So we want to apply that to a picture like this. So here's what we're going to write. And this is what's on page 106, although they do a different version. They say these are the 3 ways something can be discontinuous. I'm going to write down the 3 things it takes to be continuous, and if it violates any of those, then it's discontinuous. So a function is continuous at x equals a if, all right, and then there's going to be 3 things. First of all, f must be defined at a, at x equals a. F must be defined at x equals a. Now what that means is there must be an output. If you want to put that in parentheses there or something, there must be an output at that point. Now, what would be examples of graphs that wouldn't have an output at a point? Well, no, square root of x has output everywhere in its domain, right? I mean, 1 over x. The graph of 1 over x has a vertical asymptote, right? There's a place where it's undefined, right? Like at x equals 0, right? That'd be the graph 1 over x. So if you had a vertical asymptote, the graph's undefined. Where else would be what kind of graph? What could happen in a graph where there's no output there? What about a hole in the graph? Right? There's a hole in the graph. Now, there couldn't be another dot somewhere, right? There would have to be just a hole, and there's no value there. Okay, so those would be the 2 examples for that. Okay, so clearly, if that happened, then it would be discontinuous, right? So the function must be defined. It must have an output. Okay, second thing, the limit as x approaches a of f of x must exist. Okay, the limit must exist. Now, what would a graph look like where the limit does not exist? Like a break, right? Like that break we talked about, right? So you could have a graph coming in like this, and then going like that. There's some break. Clearly, that function is not continuous. There's something weird going on. Okay? And, well, actually, wouldn't this 1 over x example work too? Now, we're not going to focus so much on the asymptote ones right now. But if you had a vertical asymptote, the cars don't meet either, right? I mean, that'd be another kind of break in the graph, would be a vertical azimuth. So a vertical azimuth would fail both of these situations, okay? But a hole, that wouldn't fail number 2, right? The limit exists here, the cars meet. So the limit exists here, but it doesn't have an output. Here it has an output, right? In this example, there's an output everywhere, right? So it doesn't fail number 1, but the limit doesn't exist, so it fails that one. So that's why it's not continuous. Okay, and then the third one. The third one takes care of this situation. What if you had a hole and then a dot right there? Is number 1 satisfied? Is there an output everywhere? There's an output everywhere. Does a limit exist?
Yeah.
The cars would meet. So what's wrong? Well, yes, extra dot. We put an extra dot. They're not the same. They got to be the same, right? Where the cars meet has to also be where the diner is, right? I mean, that the point, the output, and where the limit is have to be the same. So the limit, as x approaches a, of f of x, has to equal f of a, which means the output of a. And we've talked about that where I said, hey, on this graph, f of 3 is 1, but the cars meet down here at negative 1. So the limit is not the same as what the output is. So those 3 things have to happen. The limit must exist, the cars have to meet, there has to be an output there, so there can't be just a hole, and where the cars meet and what the output is have to be the same. If all 3 of those are satisfied, then you've got a nice, unbroken graph, okay, where nothing weird is going on. Okay, and it's very easy to see when a graph is continuous or not, but what I want you to be able to do is give the technical reason. And so what I will ask you on the quiz is, here's a graph of f, list where it's discontinuous, and so you guys did that already, -3, -1, 1, 2, 4, and then tell me why it's discontinuous there. And I don't want words like there's a break, there's a jump, there's a gap. I want one of those 3 right there. Now you don't have to have it word for word, but you have to say basically what's happening. So let's just take them one at a time. Why is it discontinuous at -3?
As x approaches the negative of f of x is not equal to.
Perfect. Okay. Number 3. Now don't put number 3, but say what you said. The limit. You could just say the limit does not equal. Put a line through there, or you can write it out. But the limit as x approaches -3 does not equal f of -3. The limit's down here at -1, but the output's up here at 1. So that's what we were just saying. Okay. What's the problem at -1?
Limit of f of x as x approaches, or limit of -1 as x
The-
approaches negative.
No, the limit of f of x
Oh.
as x approaches -1 does not exist. Now, I'll be honest. If you just said the limit at x equals -1, the limit does not exist, that'd be good enough. You know, I mean, that would be fine. The limit does not exist because you're telling me what's happening. Okay. Yeah, it'd be good if you say the limit as x approaches -1, whatever. But the limit does not exist. That's a problem. Doesn't violate number 1 because there's an output there. Now, if there were 2 open circles here, it would actually violate both 1 and 2, wouldn't it?
So if
Okay.
it violates both, do we need to put both?
You don't have to. I don't think you would have to. I mean, 1's good enough. If it violates any one of those, it's not continuous. So you could probably just put 1. Okay, at 1, what do you got? Limit doesn't exist again. Same thing. Number 2, or at x equals 2. No, it's defined because it's got this.
Limit does not equal output.
So the limit does not equal the output at that point, right? And then at 4, say, well, that's kind of an end point, but same thing. Now, cover up. Okay, that's not going to work. Cover up this dot right here. Okay? Now what's the problem at -3?
F is not defined at x equals a.
Not defined. There's no output there, right? So the limit exists, but there's no output if the dot wasn't there. Okay, so that would violate that. So just understand that, I mean, why is the function discontinuous? It's because of those breaks and those kind of things. But why technically is it? It's one of those 3 things. So we want to basically memorize those things. Okay? What's that? At 2 was this one. Because the limit, the cars meet at 1, but the output's down here at -1. So the limit's not equal to the output. negative one they don't meet, so that's this one. So the limit doesn't exist. Okay? All right. So what I've got for you here are a couple of worksheets on just limits. The first one here is calculator ones. And they're not really derivative, but they don't have anything to do with derivative. They're just table ones, right? Where you put them in, graph them, look at your table. On the test, I will want you to actually put down the table, okay? Yes. Yeah. I think what I said on that is there's going to come a time here where we're going to need to kind of go back over that chart stuff and all those things, and that's when I'm going to hand those back. And we're going to kind of, but if you ever want to see your grade, or if you want to come in and see it individually and see what you missed, you can certainly do that. All right. This second worksheet are algebra ones. So these would be no calculator, using the factoring, using the conjugate method, using common denominator, whatever's appropriate, maybe just direct substitution. And like I said, if you get a 6 over 0 or a 2 over 0, for right now you can just put does not exist. Okay? So we'll spend some time answering questions on those tomorrow if you get stuck on some. Kind of summarizing and reviewing for the quiz a little bit, talking about section 4. Yeah.